Hi guys, today I will go in the depth of the soft switching LLC Tank Resonator. So let's start with a brief theory. The schematic is on the left in this slide, and basically you have to provide the 0 voltage to the transformer with an half bridge or a full bridge configuration. I will use a full bridge configuration in my schematic. And then the tank is provided by the transformer parasitic features like the resonant inductor, the magnetizing inductor, and the resonant capacitor. The resonant capacitor CR is the only component that you have to add outside outside your circuit. Then these three will create a true resonance. The first is FR, and the second is FM. And you have to distinguish that the switching frequency, which the switches turn on and turn off or commutate, F switch, is different from the switching. It can be different from the resonance frequency of your tank. Based on this, you can have three modes of operating. If you have the same F switch equal to F0, you have this kind of waveform here. And theoretically speaking, if the dead time TD is almost null, like 10 nanosecond, these are the waveform that you will get. And basically, these provide the best soft switching action. We will use this configuration here below F0. So we'll set the switching frequency F switch to 400 kilohertz and F0 to 450k, more or less 400 to 60k. And these provide boost action and these provide the back action, but you don't care so much about that. These are the waveform that you are gonna expect whenever you use this configuration or not. Yes, you will have a slight change in the diode current in the rectifier, but above that you will probably get something like this. So VGS Q1 and VGS Q2 are the gate and the gate source voltage switching that you have to apply. As you can see here, there is the dead time that you have to apply in order not only to avoid the short circuit in these two phases, but also because, as you can see in the right bottom corner of the slide, as you can see, you have two conditions to satisfy in order to have the soft switching. And the first is the dead time must be greater than 6 times the equivalent capacitor of your MOSFET. Now, the MOSFET basically has this problem here. When you have a synchronous configuration like this, basically the parasitic capacitor CDS, the CDS must be depleted and undepleted at each switching period. So basically what you have to say here is that you have first you have to provide enough magnetizing energy to deplete you have to provide enough magnetizing energy to deplete this capacitor here. So let me draw again. You have to provide enough magnetizing current, which this will be the waveform of the magnetizing current, to actually deplete this capacitor here. And so the energy of the inductor energy must be greater than the capacitor energy, basically. And you have to provide also enough time to make this happen, so that time must be higher than 6 times the equivalent capacitor times the switching frequency, and etc. So expect at that time, if you're using very high voltage SiC or MOSFET, expect at that time even like 10 nanosecond, 200 nanosecond, something like that. I will show you later that if you don't do that, it won't work. Now these are the main waveform. This is the most important waveform. So the green waveform is the LR and CR resonance current. The primary current is in red, and the green current is actually the inductor and the CR resonant current. the magnetizing current is just the triangular waveform that you expect like an inductor. This graph here is quite peculiar. You can obtain this in LTSPICE just simulating the first order approximation. Your tank approximation will be something like this. Sorry, this is wrong. Sorry, this is wrong. With the load here. The load has an equation like this, and basically this is the first harmonic approximation, and n square, basically n square is the turn ratio, 8x is given by the impedance, 8x over pi is given by the impedance, so basically it is the equivalent impedance that you see on the other side. You can see that you can seek the demonstration line, but right now I don't care. So in order to verify your design, you should seek when the value is equal to 1. Here you will have your F0. So first, before doing the analysis in LTSPICE of your converter, first we have to simulate the tank. So let's use the AC, the voltage. Let's use the voltage, and let's use the tank that the value that I designed, which are specifically maybe sorry, I put let me put 4 should be enough. Let me. Okay, sorry for that. And so let's simulate first the tank. So this is LR. So my values that I simulated with sheet are what? LR. So dot param LR equal to 2 micro. Dot param CR equal to 60 nano. And dot param LM equal to 100 micro. So these are my parameters. Something is wrong. The text, let me put it red, like this. Okay, so resonant capacitor CR, and resonant inductor AC1, and resonant inductor, magnetizing inductor ALM. Now, in order to obtain that curve, you want to put the gain. You wanted to put the load, which is varying between heavy values. In our configuration, we will use very high power. So let me spend a word like this. We will have like 600 volts on the input and a power about 3 kilowatt. So we will use the full bridge configuration with the 4 switches. Yes, this one here, basically. And on the secondary side, since we will have something like 30 volts, you can expect very high current, like 100 amperes. So you have to provide a very high parallel configuration in order to sustain this high current. So in this side, you will have high voltage, low current. In this side, you'll have low voltage, high current. So this is quite interesting. But first, let's simulate the gain. So let's use the parameter R, and let's say dot step param R, for instance, 100, 200, 150, 20, 10, 5, 1. Let's call this node VO, and let's put the ground, and let's run the simulation. In the decade, and 100 points, 1 megahertz. Oh, sorry, probably I okay. So at first it may seem wrong. Okay, let me change the. I made an update on LTSPICE. So sorry. Wait a second. Pen thickness 4. It was on waveform. the track data width 4 and I don't remember how it was to keep the axis. Maybe drafting off option. No, font properties is good. Sorry, wait 1 minute because otherwise you can't see. You can't see nothing. Okay, now you can see something. Okay, but anyway, you have to put on linear, and you will obtain a graph very similar to this one here. Okay, let's exclude the phase. We don't care about the phase. Okay, actually, you have to put a lighter load like this. Okay, this is fine. And let's correct the zoom extent so you don't care about low frequency. Let's put 10K. And there you have it. So you have to search for the point in which you have 1 volt. And you have to block it with F4. Okay, as I said at the beginning of the video, I will be designing the frequency at 450 kilohertz, and as you can see in my calculation, more or less it turns out right. We have 450 kilohertz as F0, so we can set the switching frequency to 400 kilohertz, and we are free to go. So let's perform the real simulation this time, and let's put the MOSFET because we need the full bridge configuration. Okay, so here we have to be careful because we need the gate voltage from the primary and also for the secondary. So the MOSFET will be the first of the list. Let's import the tank. So this will be our tank. Now, since we want to have 30 volts on the other side, we have to put a very high impedance on this side. Oh, the dot is always on the contrary. What an asshole. So, L2 like this. Be careful at the verse. Let's put 400 milli. And let's put 1 milli here. So that you have 60 volts to 30 volts. If naturally the duty cycle is .param d equal to 0.5. Because you have also to declare this. Okay, let's import the tank with our parameters. And let's perform the full bridge, the full bridge converter. And on the other side, you need the rectifier. So in the first simulation, to make it quick, I will just put 4 diodes like this because I wanted to make a fast simulation. With a 1 milliohm capacitor and the load, a very high load. And then, even if the waveform are correct, I will show you that the diode are not feasible, and so we need to put really the MOSFET on the other side. But before doing that, we need to define the gate signals of the MOSFET. So yes, let's connect. Okay, let's connect. Oh, sorry, I forgot. Sorry, I forgot to connect the bridge. So as you can see, during the turn on, let me. Okay, during the turn on, this will be on. So it will be charging the inductor, the inductor here, like this. This is during the turn on. So these two MOSFETs must have the same, they must have the same waveform. So let me call this node A and this node B. And then let's connect this node here to A and this node here to B. Okay, so let's call this node VG1. Be careful with the names. VG1, let's call the VG1, VG1. Let me give just different VG1A and VG1B. They are the same, but I prefer different names because this is differential, so you will need another voltage source. And let's call this VG2A and VG2B. VG2B. Okay, let's put the ground here. And let's define the 4 voltages. So dot param Fs equal to 400 kilohertz. Dot param Ts equal to 1 over Fs. Dot param D equal to 0.5. And dot param Td equal to 100 nanoseconds. Just nano, sorry. Please go away. Okay, oh, sorry. I connected wrongly the. It's like this. Okay, so let's define the voltages, the gate voltages for the primary, and then we will do something similar in the secondary side. So first, VGA A and A. This is the main. This is the main, and will be parts between 0.5, 1 nano, 1 nano, ion D times I don't know if I have to define the D over Fs. Yes. T period 1 over T period of Ts. Ion, this will be minus Td. Now, this is the same, but grounded. And the name is B. These two are the same. Now you need the other two. So let me copy this one. And it will be between VG2A and B. Now this has to be translated, have a delay D over Fs. And the on period is 1 minus D, which is useless because I set the time to 0.5, so it is basically useless. Let's copy this one. And let's put the ground, and let's call this node VG2B. Now, if I made everything correct, I shouldn't have any kind of mistake. So let me check for a moment. but it should be good. Let me save this file as LLC soft switching. And let me save this file just LLC Tank Only. We can close this and we can run this. For 1 millisecond should be enough. Okay, so no mistake in the run. This is quite good. So the first thing that we wanna check is the gate voltage. Okay, don't jump immediately to the output voltage, okay? You can find ugly surprises. So first, let's see this. Oh, so bright. Don't know what happened to my LTSPICE, but it is so bright. So these two must be the same. Okay, good. And between this one and this one, there must be a dead time of 150 nanosecond. Seems legit to me. Okay, this is good. Okay, now we have to check the primary voltage. It must be between it must be between minus 60, minus Vin, and plus Vin. And this is true. As you can see, it is between minus 60 volts and plus 60 volts. Yes, the waveform is quite strange. Yeah, it is quite strange indeed. But we can say that it is holding to the theory. Now let us check the magnetizing. Okay, so something is wrong. Something is wrong because you can't have that. So what is happening here? I am saturating the transformer. Yes, because this is not a transformer. I forgot to say K, L1, L2 equal to 1. The simulation was a bit fast, in my opinion, okay? Okay, let me check. Okay, let me check for a moment. Ah, no, sorry, put VO equal. Ah, okay. When I imported the tank, I forgot to count the node. Sorry. Okay, no, so now it is okay. So now the waveform is what it should be. So actually, I'm gonna waveform, and let's check the CR waveform. Okay, so as you can see, we immediately get that we are getting very close to the waveform of the theory. You see that we are in this condition here when the switching frequency is below F0, and so we have the ER, which is following this path here, and then it will follow exactly the magnetizing current. So for an interval, it is for this interval here, which is in the dead time, it will follow the magnetizing inductor. So we are so the design is correct. But if you check the source current of this, it is quite strange. No, it is correct, even this. Okay, as you can see, it starts from a negative current, and then you have this kind of... it is not exactly a soft switching here. Not exactly a soft switching here, because the condition will change with the... Okay. So, sorry. Let me start saving data, 400 micro, and let's put to 420 micro. Sorry, but it's infeasible to each time that I have to zoom out in, I will go mad. Okay, so even the switching waveform resembles the theory. As you can see, I have IQ1, which starts from a negative interval, and then it will ramp up to a quasi sinusoidal waveform, and then it will have this small interval here, as you can see, and combined with this, unfortunately, it can hard switch. In this little period here, it can hard switch. How can you say that? Just check the power. If you will see the high spikes, you will see. Okay, the spikes are not so high. So yes, it is in that interval here, it is hard switching, but not so much. And the dissipation is 6 watts, which is very, very high. So let us check the output voltage, which is 28 volts. And the power is about 3.2 kilowatt at the input and at the output, sorry, and the average power is 3.4 kilowatt. So let me make 3. Let me check again, sorry. 3.4 kilowatt. So let me make a very simple calculation. So we have 3.4 at the input, and at the output we have 3.2. The dissipation, the efficiency is quite low. 3.2 over 3.4, 94%. We have 94% of efficiency. According to you, it is an high or low efficiency? I give you a second. A very low efficiency. Why? Because having 94% of efficiency means in practice that if you perform the subtraction, you see 94 efficiency, wow, so very high. No, it is terrible. Because you have 3.4 minus 3.2, which are basically 200 watts to dissipate, which are a lot. Not only in the switches, but also in the secondary. As you can see, the diodes are dissipating 50 watts, which is basically a heater, so it is not feasible to have diodes on the secondary side, like I said before. The waveform are correct, yes, but it is not feasible to have the diode on the secondary side. Let me check also the primary waveform, the secondary waveform, sorry. As you can see, it is between V out minus V out, so minus 30 and plus 30. You have to verify that the average voltage is 0, and it is 0. Otherwise, it will saturate. Also for this one, okay? Let me check, and it is 5 millivolts. Yes, it is 0. By the way, it is 0. And I can close the video here. I could close the video here. I could. Because this is the LLC Tank Resonator waveform soft switching, and it is quite correct. But there is a big problem. And first, not only that these are MOSFET which has a VDS of 30 volts, and here I put 600 volts. So you should choose a MOSFET which a SiC probably, which can sustain these high voltages, even more than 600. I can't do that right now, because if I do that, everything will change. Remember the equation that I said at the beginning, that the energy of the inductor must be greater than the equivalent capacitor, which is right here. Well, if you change the MOSFET, you will change the COSS of the MOSFET, and so everything will go away. I will have to do the design all over again. So don't think that to take this SPICE and substitute everything, it will work. No, if you want to take this SPICE, which I will give to you, you have to cancel this, and also you have to substitute your own value here. The waveform are fine, are correct, just put the parameter that you want, but you have to substitute the MOSFET and your own values. Otherwise it won't work. You don't believe me? Just change the MOSFET with this, and nothing will work. See? I have something completely different. Okay, I have this huge spike for no reason, but aside from that spike, everything seems normal to me. And okay, it seems that I have even an even soft switching like imagined, because it does tuck and then goes to 0 here. No, it doesn't go to 0. It is 1 amp. So okay. And but anyway, so I can say let's do this. LLC soft switching. I can save this file. I will open another file and copy everything. But this time I will do the secondary side. So I will also design the the DC, sorry, the AC to DC active converter. Synchronous converter, sorry, because this is passive. So how can you design when you are in this situation here, which you have the high voltage and high voltage and low current from one side, and in this side here you have low voltage and high current. How can you design an AC to DC converter? Well, basically, you have to first you have to know when one waveform is active. You have to know the path of the current and the right time. What does it mean? So we can we can delete everything. So during this time here, oh, you see that when this is active, the current will flow here, and then it will go here. As you can see, the current is the same. So I expect, yes, it is the same, but I expect that during this time, the positive current is rectified. So you have to follow the same path. And so this current here, okay, is positive. Which of these two paths is positive? This. It goes here, here, into the load, and goes here. So, meaning that if I click on the current of ID1, I expect ID1 to be in the same interval of ID of N1. If that's the case, you can toggle these two MOSFET and these two diodes and put the MOSFET with the same gate voltage of this. In this way, you will have that when this MOSFET is on, also this MOSFET is on. Let's check if this is true in the waveform. And as you can see, ID1 is active in the same time when IM1 and IM4 are active. The current will follow this path here, and ID4 is the same. So, we can remove these two MOSFET here. Again, MOSFET, puerco diablo. Diodes. And let's call this node C. And let's call this node D. Let's put the MOSFETs here. And even here. Now, in this case, you don't want to pick a MOSFET with an Heron of 20 million. Why? Because, as you can see here, you have a very high current. So most of the dissipation, you do remember that the dissipation of the MOSFET is given mainly by two contribution. So the P dissipation is given by P cond, which is equal to R ohm Rs times I square, and the P switching, which is proportional to T on, T off, TD, COSS, blah 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 blah. And this contribution here is very high when the current is high. So you want to keep this RS as low as possible. So this time, let me choose a MOSFET which has very low Aron, like the AO. But of course, it has to be like the AOE. No, I can't write it. I had to choose a MOSFET with low. Okay. No, 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 no. Okay, so we're on 0.8 and get charged quite tight, but we can choose this because it has a very, 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 very low Aron. This can be very useful. Okay, so you want to make a very, very, very high current capability here. So you have to put more than one in parallel, okay? Otherwise, you won't be able to sustain so much current. But first, let's put the main 4. As you can see, it is very similar to the full bridge here, okay? But it is in the other direction. So let me call this node here VG free C, and it has to be the same, so VG free D. This is VG 4C and VG 4D. Now I have to be extremely careful in not making any mistake. So VG1A, this one is the same as this. So this one is the same as this. Because one mistake and everything falls apart. So you have to be extremely careful and concentrated. And this is the same as 3D. Now the 4D, the remaining 2, which is this, and also this is differential. And the last one, which is this, grounded. Now, I should have made everything correct. So let me save file as LLC soft switching synchronous sync rectifier, because this is a synchronous rectifier. Let me run the simulation and pray that everything is fine. Run. Oh, let me check the output voltage. Yes, 29 volts. And as you can see, the output voltage is increased by 1 volts and half, because I don't have the drop of the diode, which in this case is very high. So this is good. Now let us check the waveform. And as you can see, are the same as before. So nothing has changed, you may think. But the advantage of the MOSFET is that you can make the parallel of them. So as you can see here, are we performing zero current? Well, the answer is check yourself. When does it start to switch? It starts to switch at 1 amp. Okay, so it was almost near to zero current, but almost. The dissipation is horrible. 12 volts. 12 watts. Let us check if we kept the same, according to you, are we keeping the same waveform on the primary? The same waveform as this? Do you expect to have the same as this? Oh, sorry, this is the contrary. The answer is no. Because the parasitic on the secondary side will be reflected on the primary side. So what happens is that during the dead time, which is here, you're gonna have some resonance. Let us check if this is true. And of course it is. As you can see, during the dead time, you're gonna have some resonance. And if you analyze the frequency of this resonance, is around 56 megahertz. So it is given by the parasitic of the secondary side. And you can also see this on the secondary side current, which has this resonance here during the time. But now we can reduce the power dissipation with the paralleling. So this is very big. So this is very big. Yes, this should be big enough. So we need at least 3 of them. Like this. No, something is not... okay. Sorry. My bad. Ooh. Be careful to the schematic. Be careful. Okay, so this is the number 3 also for D. And also for this guy. And also for this guy here. And for the last guy, this one, and this one here. So this is now the complete synchronous rectifier. And we should be able to sustain that power that I ask, which are 3 kilowatts. So let me run the simulation again. And we shouldn't have any more 200 ampere flowing into... we have 80 amperes, which is feasible for one MOSFET. It can be feasible. And the dissipation of this is 1.5 watts. So we have reached a feasible dissipation in this case, and we have kept all the waveform more or less. We have kept all the waveform of the switching frequency. Oh, I hate when I click the current and he always give the contrary of the current that I want. Whoa! I want this? No, negative. Why? For the inductor there is a reason, because for the lens inductor you wanted to do the opposition, but so the parasitic have increased, as you can see, but overall the waveform is kept all together. So I think, guys, thank you for the... 1 year ago I made a video about the LLC, but it was a disaster, okay? Now you have a true video of soft switching LLC Tank Resonator. You can enjoy, you can use both spices as you prefer, you can play with them. Naturally, this is only as this is only for educational purposes. So use this spice just to learn about the waveform and to understand how it works. The flow of the current, the power dissipation, the soft switching, everything that you want. For the design, it requires a lot of time and it's way harder. So thank you guys for this. Thank you guys for the comments, and I will see you in the next video. Bye bye.